Okay, so what I want to discuss basically this week, I don't know how much else I'll get to. Excuse me. What I want to discuss this week is convergence of Fourier series. Okay, and this is actually a very delicate question. Beginning with what does it mean when we say Fourier series converge? So what we have said so far, we're going to be looking at the full Fourier series. So we're going to have some function f. This is going to be defined on minus pi to pi, and you can remember the full Fourier series is going to be given by 1/2 a0 plus the sum from k equals 1 to infinity ak cosine kx plus bk sine kx, and then the ak coefficients are given by 1 over pi times the integral from minus pi to pi f of y cosine ky dy, and then the bk's are given by 1 over pi times the integral from minus pi to pi f of y sine ky dy. Okay, and so the question is, does this equal f, or in what sense does this equal f? The better way to ask this though is to put it in here, so we're just looking at a finite sum. Okay, if I put it in there, everything is well defined. And let's call this S sub n of x, meaning the partial sum. And so the primary question that we're going to answer, that we're going to ask is, in what sense does the partial sum of the Fourier series converge to f? Okay, so we're kind of thinking about f as being fixed. So of course for every f, we're going to have a different Sn. So this Sn depends on f. And so the question is, in what sense does this convergence happen? And does it happen in any sense would be another question. Kind of a hidden underlying question. Okay, so what do I mean in what sense? Well, what are different senses in which a function can converge? In which a sequence of functions can converge to a function? Well, the most familiar and intuitive one would be pointwise. So pointwise means the following. Pointwise means for every x, and just because I don't want to keep writing, our universe is basically going to consist of minus pi to pi. Now we're going to be looking at periodic extensions of this function to make the proof work. And in that sense, maybe we're going from like minus 3 pi to 2 pi or something like that. But when I say for every x, I mean every x in minus pi to pi. So for every x, I can form this sequence, Sn of x. Okay, so x is fixed. I'm looking at these partial sums, evaluating at x. As long as n is finite, this partial sum is perfectly well defined, and there's nothing, ambiguous here. So this is a sequence of real numbers, and so pointwise means that for every value of x, this sequence of numbers converges to f of x. Okay, now the theorem, we haven't proved it yet, but we know in the theorem this is not going to be true for all f. It'll be true when f is continuous, for example. But if f has a jump discontinuity, this is going to converge to the jump, the average of the two jumps, which is about the best that we can assume. So this is pointwise convergence. A slightly weaker version of this, a slightly weaker version of pointwise convergence, I can't say exactly what it means, because we don't have, not everybody has the background, but it means this holds, it converges pointwise for almost every x. Okay, so for almost every, for AEX, we have Sn of x goes to f of x. Okay, so almost every is a term from the theory of measure theory, from the theory of measure theory. Come on, dude. Almost every is a term from measure theory, and it has a precise meaning. So what this means is that this equality holds, or this convergence holds, except for perhaps on a set of measure zero. Now, a set of measure zero is hard to define without talking about measure theory, but it basically just means a set of measure zero is going to be a set a small set. Like an isolated point is a set of measure zero. A set of isolated points. That is, if you have a set of isolated points and you can draw like a interval around each point that doesn't intersect any of the other intervals, that's going to be a set of measure zero. Any countable set is a set of measure zeros. So rational numbers are not isolated, but the rational numbers do form a set of measure zero. Okay, so sets of measure zero in some sense can be big because the rational numbers are dense, but in some sense they can be small because it's a set of measure zero. And if you want to know more about measure theory, ask in the discussions. But we're not going to talk too much about this. The major theorem proving almost everywhere convergence. This is a huge theorem that wasn't proven until I believe 1966 by Carlson. And then a little bit later, a new proof, I forget what year, I think it was still in the 60s, but I'm not completely sure. It actually might be in the 70s, I don't know. Was proven by Charles Pfefferman. Now, both of these guys have won the Fields Medal. So the reason I mention that is because proving this almost everywhere convergence for a general function f is very difficult. In fact, you win a Fields Medal. Carlson actually won the Fields Medal for proving the almost everywhere convergence and one other thing. And Pfefferman didn't win the Fields Medal for the almost everywhere convergence. He won it for something else. But the point is, you got to be, top tier level mathematician apparently to prove this theorem. This is a very difficult theorem. We're not going to talk about it. I will say, if you're interested to read, if you do want to know more about this, kind of one of the most streamlined proofs was given in the I think the early 2000s or the 2010s. This was given by Lacey and Tila, and then Lacey kind of has just an expository paper on this. The paper that Lacey and Tila wrote is very terse. Lacey kind of wrote a more leisurely paper going over the proof. Anyways, it's all very difficult though. It's in an area called time frequency analysis. All right, so 3. What's another way that we can converge? Well, we can actually make this a little bit stronger. And we can actually insist that the rates of convergence for every x are kind of uniform. So what I mean by this is for all epsilon greater than 0, there exists an n prime. So remember, backwards e means n prime. There exists an n prime such that if n is greater than n prime, then Sn of x minus f of x is less than epsilon. You're probably going to have to pause the video and think about what's going on here. Okay, but what we're saying is so what does this say? So if I just look at this, it's for for all x, so I'm saying for every x, this is true. So for every x, this is true. So what does it mean for Sn of x to converge to f of x? It means for every epsilon, for every epsilon greater than 0, there is an n prime such that if n is bigger than n prime, Sn of x minus f of x, the absolute value of that is less than epsilon. But the key thing here is that the n prime can depend on x, but here the n prime cannot depend on x. So the functions are uniform. So the sequences are the sequence of functions are uniformly converging to f. Okay, so one of the best ways to explain the difference between pointwise convergence and uniform convergence is to give an example of a sequence that converges pointwise but not uniformly. I'm going to erase this stuff over here because I want to talk about these modes of convergence. Okay, so let's look kind of a simple example. We'll say this is pi and this is 0. We will forget about minus pi. I'm just going to show the difference, an example of a sequence of functions that converges pointwise but not uniformly. So let's say this is equal to 1 over n. So I'm going to give the graph of the nth function in the sequence. This is 1 over n. This is 1. We're going to look at the function, the nth function, the graph of the nth function is going to be this triangle with base going from 0 to 1 over n and height at 1. Okay, and so what's going to happen as n increases, we're going to get stuff that looks like this. And if we look at another, if we keep on increasing n, we're going to get something that looks like this. Okay, but the point is, and if I started at 1, maybe I'd be all the way out over here. Okay, I guess 1 over 1, well, whatever. I guess if I started at 1, it'd be 1, so somewhere here. But anyways, nothing is to scale. The point is, this is the nth function. Okay, this is something a little bit bigger than n, something a little bit bigger than that. And so, for all, for any function in the sequence past this purple one, it's going to be 0 all there. Okay, if I look at the blue one, okay, for all of the functions in the sequence, it's going to be 0 here. Okay, so convince yourself that this sequence converges pointwise to 0. That is, for every x, eventually the leg of the triangle is going to move past it, and then from that point on, if you look at any function in the sequence, the functions will be 0 there. So this converges, I'll call it t sub n of x for triangle. So t sub n of x converges to 0 for all x. So t sub n of x converges to 0 for all x. However, notice that if I do t n of x minus 0, so just the absolute value of t n of x, and I look at the max, okay, t n is continuous, so this makes sense. If I look at them in the max, 0 less than or equal to x, less than or equal to pi, notice this is always equal to 1. So this is not the triangle functions are not uniformly shrinking to 0. They're only shrinking to 0, for each x it's going to 0, but they're not uniformly going to 0. Okay, so this is the difference between uniform convergence and pointwise convergence. Okay. Another mode of convergence. Okay, there's different ways to write this mode of convergence, or there's not different ways to write this mode of convergence. There's different types of convergence, but basically it means the integral converges to 0. So we'd have something, or the integral converges to the function. So we'd have something like the integral of the absolute value of Sn of x minus f of x goes to 0. So the integrals go to 0. Okay, and all of these modes of convergence are different. Some of them imply others, but they're all different modes of convergence. Okay, and sometimes we have just nothing there, and sometimes we'll have a 2 there. If you want to think about it in terms of maybe least squared, that's what we'll be thinking about. But this would be another way of another mode of convergence, saying that Sn converges to f if this integral converges to 0. Okay, and the one we're mostly interested in is when we have a 2 there. Okay, you might remember least squared. Okay, this is a sort of a least squared type of thing. Okay, so let's look at some more examples here. So notice that if I want to do the integral, so the question is, these functions converge pointwise to 0. Do they converge in this way to 0? Okay, well let's do the integral of t of x squared dx. Okay, and if it converges in this sense, this should be going to 0. Okay, so let's see if it converges in that sense. Well, what is the integral going to be? Well, so I just realized. I'm going to punt and let you guys do this as an exercise, and then look at a simpler example in a minute. So let's just put this back with a 1. Okay, so now, just because this integral is easier for me to compute, and I'm lazy. Okay, so t n of x, I'll do an example with the 2 there in just a minute. So what is this integral going to be? Well, it's just going to be the area of the triangle, which is 1/2 base times height. So 1/2, the base is 1 over n, and the height is 1. Okay, so this goes to 0. Okay, so in other words, this set of sequence of functions, it converges pointwise to 0. It also converges almost everywhere, because if it converges pointwise everywhere, that means it converges pointwise almost everywhere. It does not converge uniformly, but it does converge in this integral sense. Okay, so let's modify this example a little bit. So let's say that, see if I can. Let's modify this example a little bit. So this is 1 over n, and let's say this is n. Now this is really going to not be to scale. And now let's look at the next one. It's going to be something like this. I'm just going to draw one more example. So this is going to be, I'll say 1 over n prime, where n prime is bigger than n. And now what I'm going to say that the peak here is going to be equal to n squared. Okay, now still, this sequence of functions still converges pointwise to 0, because eventually for every value of x, the leg is going to move past that x, and so it converges to 0 for every value of x. But now what is the integral equal to? Well, I still have 1/2 base times height, so the base is going to be 1 over n, but now the height is n squared. And so this is n over 2. Okay, so actually the integrals go to infinity, yet they converge to 0 pointwise. Okay, so here's an example of kind of the exact opposite things happening. It does not converge in this sense at all, because the integral of t n of x minus 0 goes to infinity. It doesn't go to 0, it goes to infinity. Yet they converge pointwise to 0. Okay, so now what have we seen? We've seen an example of functions that converge pointwise, but not uniformly. We've seen an example of functions that converge pointwise, but neither uniformly nor in this sense right here. What about the other way? Can we find a sequence of functions that converges in this way, but not pointwise? Okay, so let's look at the sequence of functions that might converge in that way, but not pointwise. Okay, so to do this, again, for these examples of functions, I'm just going to make that 1 instead of pi. For the examples of functions, it's really better to draw the graph. So the first function is just going to be equal to 1, and it's going to go from 1. So remember, what I'm trying to do is I want to construct a sequence of functions that this goes to 0, such that the integral goes to 0, but it does not converge pointwise. So I'm going to find a sequence of functions where the integrals of the t n of x's go to 0, but actually what we're going to see is t n of x does not go to 0 for any x. Okay, so this is going to be the first function. The area of this function, so this is 1/2. Actually, let me make this 2. So the area of this function, it's a rectangle, the area is going to be equal to 1, so its integral is 1. Okay, so the next function that I'm going to look at is going to be, again, it's going to be a function going from here to here. So again, from 1/2 to 1, this is the graph. Of course, the graph technically doesn't include this part here, but just to draw the box I am. So the area of both of these are 1. Okay, so this is like the first function in the sequence, this is the second function in the sequence. Okay, next what I'm going to do is the next function in the sequence is going to be the function that's going to go from, this could be 2, or this could be 1, I don't know why I made it 2, sorry. I think just so the area is always 1, but I don't know. Anyways, so I want to look at now the function that goes, it's just going to be 2 from 0 to 1/4. This is the third function in the sequence. So what is the area of this? Well, the base is 1/4, the height is 2. The base is 1/4, the height is 2. So the area is 1/2. Okay, and then the next function is going to be like this. Okay, so the area here is 1/2. The next function is going to be from 1/2 to 3/4. The area is 1/2, and the next function is going to be height 2 still, but the base going from 3/4 to 1, and that area will be 1/2. Okay, so I've now got like I've now got the first 6 terms of the function, or the sequence. Okay, so I'll just give the next few terms. Okay, so now I'm just going to have the integral going from, or the box is going to go from 0 to 1/4. Okay, so this would be like the 7th function. Okay, sorry, 0 to 1/8, and it's height 2, so the area of this is 1/4, and then the area of this one is going to be 1/4, that one, that one, that one, that one, that one, that one, so on and so forth. And so what happens is that the graphs are just going to be these rectangles that are getting skinnier and skinnier, moving from one side to the other. And the area of the rectangles goes to 0. So it means this integral goes to 0 because the area of the rectangles are going to 0. Yet, for any value of x, there's going to be infinitely many of these rectangles that pass by it. And each time a rectangle passes by it, the value of the function there is going to be equal to 2. So here's an example of a function that converges in terms of the integral, but does not converge pointwise. Okay, what about a sequence of functions that converges uniformly? If a function converges uniformly, it definitely converges by 1 and 2. But does that also mean that the integral is going to go to 0? Okay, and the answer is yes, as long as we're dealing with a finite interval like this. In terms of measure theory, we'd say a space of finite measure. And the reason is pretty simple. If I have Sn of x minus f of x, let's just say back to our original context, minus pi to pi. If the convergence is uniform, this means I can choose n so large that this difference, no matter what x's I put in here, will be less than epsilon. So I can always make this be less than epsilon times the length of the interval, which is 2 pi. Okay, and so in other words, I can make this go to 0. Okay, I can make this arbitrarily small by taking n arbitrarily large. Okay, on the other hand, if I look over, let's say, 0 to infinity, if I look at 0 to infinity, I no longer have this, right? Because if I look at the integral from 0 to positive infinity of Sn of x minus f of x, well, if Sn of x converges uniformly, this is definitely going to be true. I can make n large enough so that this difference is less than epsilon, but now I'm integrating over an infinite space, so this integral is just equal to 0. Okay, so an example of a sequence of functions that converges uniformly, but the integrals don't converge, is going to be sort of maybe the opposite of the things that we've seen so far. So let's say the first function, the graph of the first function, it'll be 1 here, and it will go out to 1 here. The next function is going to be 1/2, and it's going to go out to 2 here. Okay, this is badly not to scale. The next function is going to be 1/3, and it'll go out to 3 here. Now the area of each one of these rectangles is going to be 1. So I will call this Tn of x again, even though they're not triangles. So Tn of x, the integral of Tn of x for all values of n is equal to 1. Yet the absolute value of Tn of x for any x is less than or equal to 1 over n. So in other words, this converges uniformly to 0. Okay? And convince yourself from the definitions that if Tn of x is less than or equal to 1 over n, this converges uniformly, by this definition here. They're uniformly getting smaller. I mean, you can see from the graphs here, the functions are uniformly getting smaller. There's not like a peak out here where it's bigger. The functions are uniformly getting smaller. Okay, even though there's some points up here which are, the point way out there is going to be 0 for a lot of terms in this sequence, and then it's going to eventually get to some point. Like if this is 1,000,000, okay, once we get to say the 1,000,000th term of the sequence, the function there is going to be going to go from 0 in the 1 million minus 1th function to being equal to 1 over a million at the millionth sequence, and it's never going to be 0 after that. It's going to slowly shrink down to 0. Okay, but the point is, this is true. And since this is true, since this inequality is true for all values of x, we have uniformity. Like the right-hand side here doesn't depend on x. Okay, so here's an example of a sequence of functions that converges to 0 uniformly, but not in terms of integrals. Okay, so the point of this video is basically to introduce you a little bit to the different modes of convergence that we call them. And just to point out that we do have something a little more subtle going on that we need to take care of. So what we're going to prove in this class is that if f is continuous, piecewise continuous, if its derivative is piecewise continuous, and if it satisfies some condition at the boundaries that I'll talk about in the next video or in upcoming videos, then the series will converge pointwise to f of x, where continuous, and where it's not continuous, it's going to converge to the average of the jumps. Actually, the main thing that we're going to prove in this class is that if f is continuous and its derivative is continuous, and it satisfies this other condition at the boundary that, like I said, I'll talk about in a moment, then Sn of x is going to converge to f of x for every value of x. Okay, okay, that's it. That's it for this video. I know this one was kind of long, but again, I just wanted to point out these different modes of convergence.